Okay, welcome to the next video in systems programming. Now, I think in the past video I said that I would go next to chapter 1 of the textbook, but I realized there is a chapter 0. So why not, let's just go ahead and do that first. So let's dive into the fabulous world of computer systems. We are going to understand what a computer system is and how it runs programs. So we're going to be writing code in C, which is a high-level language, but we'll also understand how that gets turned into instructions, right? In an instruction set architecture, we will then understand how that gets transformed into bytecode, and then that can be run on the computer, and so on. I'm probably doing what I always think is kind of ridiculous about a lot of these sorts of systems books, which is that I'm probably saying a certain amount of stuff, explaining things that you don't know in terms and concepts that you also don't know. So what's the point of all of this? I think, like this book does it too. It's a little hard to resist, because you want to somehow give like an overview of everything, but, how do you do that when the reader or the viewer kind of doesn't know anything yet? I mean, that's the whole point of learning this stuff. So anyway, so why even give this overview? Well, at the very least, let's just get through chapter 0. Okay. So what is a computer system? Well, a computer system is something that combines hardware and a special system software, which they almost certainly mean an operating system. So it's basically a combination of hardware and an operating system. It has to have these components, which is an input-output sort of set of devices. Inputs are usually a mouse and keyboard. It could also be a microphone or some other input devices. Output devices are usually a computer screen and a computer speaker. You could also have a printer or, a number of other possibilities. Then next, it has a CPU, central processing unit. It runs instructions and computes data and memory addresses. What does it even mean to compute a memory address? Again, right, explaining some concepts in terms of other concepts that probably the viewer doesn't even understand. So what's the point of all of this? But okay, continuing. RAM is a certain kind of a memory, but it is extremely fast. It is extremely close to the processor, but an important feature of it is that it is it loses its memory when the system loses power. So when you cut the power to your computer, you lose everything that was in RAM. And so that's why we need these secondary storage devices. That's actually how you can, turn off your computer, unplug your computer, and then later on turn it back on, and it remembers, something, right? It has saved files and stuff like that. That's only possible because you have these secondary storage devices that keep their information even after the power has been cut, but they tend to run slower. So like each version of memory, right? These are two versions of memory, two kinds of memory. Each one has their own advantages, right? RAM is fast, but it cannot remember things after the power has been cut. Okay. All of that was hardware, and then we have this one basic piece of software, which is the operating system. You probably know some operating systems like Windows, Mac, Android on a mobile device, other mobile operating systems. Those are all instances of operating systems. Basically, what they do is they give you a user-friendly interface to your programs, right? So when you're using some program, how did you get it, right? Probably you booted up your computer and there was some icon, and that icon is basically hosted there, right? It's you can interface with it like that. because of the operating system, right? So if you think about like on a Windows desktop or a Mac desktop or whatever, and it has these icons, that's all being managed by the operating system. What would it be like if you didn't have an operating system? Well, probably you would just have like a terminal, which basically means a mostly blank screen with a little blinking cursor, and you would type your commands into the computer. And even that's a little bit more user-friendly than some other things that could possibly be done that are very ancient and we don't need to talk about. But in any case, so that's basically the concept of an operating system. Okay. And this diagram here, because I converted this from from the web page to a PDF so that I could annotate it like this, well, it cut it into pages, and so it cut this diagram in half. But let's look at the diagram on the next page. So basically what it's showing you is that there's this program at sort of the highest level, but in between is the operating system. But the operating system is like in basically direct communication with the hardware. And the hardware roughly has this breakdown of CPU, RAM, and disk. Okay, so there's that. There are lots of computing systems. We will be interested in general purpose computing systems. You can think about like a calculator that is not general purpose, right? Maybe you can tell it to add numbers, maybe you can tell it to multiply numbers. If you have, there are some programmable calculators, but like just thinking of a basic calculator. Well, those are not general purpose, right? They are not meant to receive novel instructions, right? It's not meant for you to, or to compute every possible computable function. I guess that kind of inspires the question, computable functions. Okay, so like there's a whole bunch of functions in the universe. Some of them can be computed by a computer. Are there any that cannot be computed by a computer, or is a computer able to compute every possible function? Turns out there are non-computable functions. So when we say general purpose, we don't mean every possible function. We just mean the functions that can be computed by a computer. What are the functions that cannot be computed by a computer? They're very strange. We will not be studying anything like that in this course. That is the kind of thing that you do talk about in like a theory of computation course, but we don't need to worry about that for our purposes. Okay. Also, we will be interested in reprogrammable computers, which again, maybe you think like, well, that's a little strange, right? Isn't every computer reprogrammable? Well, no. I mean, again, like your calculator, if you regard that as like a computer, as long as it doesn't have like instructions to write, like it doesn't have a way to write programs into the calculator, which some do. But if it doesn't, then it's not reprogrammable. There are ancient examples, like there is this Antikythera mechanism from ancient Greece, which is like these, interlocking rings of metal that were used, I think almost certainly to compute the positions of stars, probably used by like ancient navigators on the seas, using stars for navigation. Well, that's got an input, right? You spin, I guess, the rings of metal around to somehow indicate either like the current time or something like that. And it's supposed to output the position of the stars and help you to navigate somehow. Well, that's a computer, basically. It's got inputs and outputs, basically. But it is not reprogrammable, right? You cannot give it instructions for a new function to compute that it wasn't originally designed to compute. So there are, so to speak, non-reprogrammable computers, but they're ancient, and that's the big novel innovation of Turing, right? Like Turing was the one who came up with the idea of a reprogrammable computer. He invented it as a mathematical concept in a Turing machine, and that was possibly his biggest, most important innovation. He had many, but that one might have been the biggest one. It's really, that was the thing that was necessary to get us to the current age of computers as we understand them today. So we are, of course, only interested in reprogrammable computers. Anyway, Okay, for this stuff and this stuff, I don't have that much to comment on. You can read through the textbook. It's basically showing you what computers are like and talking about, trends in computing tending towards smaller and smaller devices. Okay, I think we're all familiar with that. But this right here, talking about multi-core processors, that is quite important. So let me get a little sort of chatty about that. You may or may not have heard of Moore's Law. So for those who have not heard of Moore's Law is basically the idea that for a long time, for many decades, it seemed like if you waited about 5 to 10 years, whatever was the state-of-the-art computer at that time, you let 5 or 10 years go by, and you can do the same amount of computation in a device that was like half the size, right? So basically the power of computers is getting bigger and bigger, right? You can take the same amount of power and pack it into smaller and smaller devices, which means that, either you can get smaller devices, or for a device of a fixed size, you can put twice as much power in it. Whichever you prefer, whatever. But the point is that basically the power of computation would double, I guess, about every 5 to 10 years. And that law seemed to hold really phenomenally accurate for several decades. But as of recording these videos right now, this is exponential growth. It's got to end sometime, right? Nature basically never has indefinite exponential growth of anything. So this law has got to come to an end at some point. And as of recording these videos right now, it seems like we are definitely in the slowdown. Devices are not getting that much more powerful that fast. They're still getting more powerful, but not nearly as fast. And so we can't, so we used to kind of depend on, well, if something is just barely outside the reach of modern computation, give it a decade and then we can do it in a future computer, but we can't depend on that sort of thinking anymore. Does that mean that we're headed towards a slowdown and that computation is just going to be a boring future from now on? No, it just means that we're not going to be dependent on the physicists and the engineers to make tiny, tiny transistors. Basically we knew that about now is when Moore's Law would sort of start coming to an end, because we are just reaching the physical limitations. We're building our transistors at the scale of atoms. So, once you get down to that, you can't make things smaller than that. And don't worry about quantum computing, because that's very interesting, but it's not going to solve Moore's Law. That it's solving a different problem. But so basically, we're just reaching the limits of physical possibility when it comes to transistors and tiny computer components. But that doesn't mean that computing is going to get boring or slow down or plateau or whatever. It just means that we have to get our innovation somewhere else. So for instance, one thing that I hope we learn about in this course is RISC-V, instruction set architecture, right? It's a relatively new innovation in how logic circuits are constructed and put together, and basically it's just performing better than its predecessor. Long story short. So that's just a way of taking the same hardware, but just using it in more efficient ways. That's one way that we're going to get more innovation and continue to advance computation into the future. Well, another very current, very popular way is with multi-core processors, right? I'm now finally getting back to talking about multi-core processors. So if you imagine that a processor basically has this job of processing data, right? It grabs some data here, is supposed to compute some kind of computation, and then store the result somewhere else. Generally, that's roughly what your processor is up to. But, often it happens that the queue, right, the sequence of things that are being given to the processor to process gets bigger and bigger, longer and longer, faster than the processor can process, right? So the processor is running just as fast and hard as it can, but the things the jobs that it needs to do is growing faster than it can process. Well, what do? Well, if Moore's law is no longer applying, you can't just build a faster processor. So maybe the next idea is, well, let's just have two processors, right? Like just have a second processor to take the weight off of that one processor. Well, that's a great idea. That's exactly the concept of a multi-core processor, but that introduces a huge amount of complexity because, imagine if that first processor edits some little information somewhere in memory. But the second processor is not a sentient being. It doesn't know that happened. And so if it is expecting that memory address to hold the old information, and this happens a lot, we'll get into actually doing these things and you'll see how it can happen, maybe, I hope. But the second processor is expecting the old information in some sense, but the information has changed. And this can lead to, destructive errors in your computer. So you need to be very careful about exactly how you design these multi-core processors. So we'll be learning about that. And so this is the whole topic of how to do proper parallel execution. So there's that. Okay, what are we going to learn in this book? It's how a computer runs a program, which in short basically is kind of what I described earlier, which is how the high-level C program gets translated into lower and lower level information storage formats or something like that, and eventually gets to the point where it's something that your computer can run. We'll learn how to assess the performance of a computer and how to use parallel computing. So that's somewhat the plan. Sort of advice about how to use this book and how to follow along. We will be using throughout a Linux operating system. Linux is, I mentioned Windows and Mac. Linux is this absolutely fantastic alternative, a free open source alternative to Windows and Mac. You can possibly install it on your own computer. When I switch over to doing the programming assignments, I just have a Linux computer. It has no operating system other than Linux. On some physical devices, you can have two operating systems kind of installed parallel, and you can switch from one to the other. If you want to do that, you of course are free to do whatever you feel like. Another option is to have a virtual machine. So this is available on both Windows and Mac, where from within Windows, it has a little, it basically creates this sub-Linux system running inside of Windows. I find those to run painfully slowly and cause all kinds of problems with, exactly what information is stored where and so on. So I hate virtual machines, but it's a common solution. And so you're free to do it. You're free to research it if you want to do it on your end. But if you're this serious about programming that you're, studying systems, maybe you just want to get a Linux computer, right? Just ditch the other operating systems and switch to Linux. That's what I went with, but of course, everybody does their own thing. But one way or another, you are going to need Linux to get through this course, whether it's a complete Linux computer or a Linux virtual machine running inside of your current operating system. You need Linux somehow. You also need C. Linux comes with C. So however you get Linux, probably as soon as you have Linux, you're already going to have a C compiler. So that shouldn't be that big of a deal. And the GNU compiler. So again, right, that's kind of, basically you have that as soon as you have Linux, probably, depending on exactly how you have Linux. But anyway, and by the way, I personally will be writing my code in a code editor, VS Code. That's nice because it does syntax highlighting and code completion and blah, blah, blah. That's not strictly necessary. You can sort of implement it, or you can edit however you prefer to edit. But that might be worth thinking about how you want to set up your programming environment. I leave that to you, and you research that. That's kind of something you're going to have to do on your own end. But you'll need these things. Okay. Once you have Linux, however you have Linux, let's go ahead and just get a little bit familiar, right? You'll see more details about this when I switch over to the programming assignments. But at least for now, know that the main way that you sort of run your C programs is you pull up a terminal, and a terminal, again, right? Recall I've somewhat briefly described this earlier, but it's going to be basically like a blank window. It might have a little bit of text, probably telling you where the terminal is currently reading the files in some directory on your computer or whatever. But anyway, the point is it should at some point have this dollar symbol. And that just indicates the point after which you are supposed to start writing your commands. So after the dollar sign, you could, for instance, write this command, uname --a. All has to be exactly like that. These are very strictly written things. So what does that do? Well, this is the command, and this is called a flag. So the command is, more or less the main thing that you are asking your computer to do, and the flag gives little settings and options and stuff like that. By the way, don't type the dollar sign. The dollar sign is where you put the command, basically, but you don't type the dollar sign. It's already there for you. Okay, anyway. What does this command do? Well, and I think when I converted this from the website to a PDF, it lost a lot of the formatting. Probably in the website, this looks much better and much more like computer code, or well, maybe not all of that, but maybe just this part of it. Anyway, so so this is supposed to be showing you what the terminal looks like. And so after the dollar sign, you type uname -a. And it prints this result, which seems like it's basically just telling you a bunch of information about your computer. So it says it's a Linux, okay, so it's telling you the operating system, basically. Fox seems to be the host name of the machine, so whoever owns this computer, they, the machine itself, you can give it a name, usually given by the user. So whoever has this machine, it looks like they named their machine Fox. Okay, and then it gives you the kernel release information, blah, 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 just a bunch of other information about your computer. That's what this command does. It's a sometimes useful command if you need to know something about your computer, like maybe you're debugging and you need to ask someone for help and they need to know some details about your computer in order to know how to help you. That's a situation where you'd want to know about this command. Anyway. But this is all just an example. What does the -a do? The -a flag prints out all relevant information associated with the system in the following order. So, maybe other options could have printed out other information, but -a caused this information to get printed out. Okay, sure. Right, and it's describing all the rest of the information that was printed out by the command. Okay. Whenever using the terminal, if you have a command like uname and you want to know, we saw what happened if you use the -a flag, but what other flags are available? Well, if you basically type man, and then the command, right? So what you would have to type, so if the dollar sign is here, right, that's where your prompt is, and you type man, which is short for manual, uname. If you type that, hit enter, it should show you usually more information than you're able to handle, but it tells you all kinds of information about the uname command, including certain flags that could go with it, and so on. So anyway, we'll get familiar with these terminal commands and stuff like that more and more as we go along, right? This should progress incrementally. So hopefully you don't get overwhelmed. If the you type the manual command and it gives you a ton of information and so much information that it doesn't even fit in the terminal. So it gives you this option to press a button to scroll to the next page of information and so on. But what if you want to escape that, right? Like you have to keep hitting the button and hitting the button and it keeps scrolling and scrolling, but it takes forever. What if you just want to quit? Well, then you type Q. Okay. So there's this appendix about using Unix. Unix, by the way, is basically like the system running underneath Linux. Basically, think of Unix and Linux as kind of very, very related things. Not exactly the same, but we don't need to worry right now about exactly what the two words mean. Anyway. Okay, then the book goes on to describe some of the book formatting, talking about how it labels certain things as asides, notes, warnings. You can read all about that. And the end, that's chapter 0. So in the next video, we'll move on to chapter 1.